have the last talk of the session, where Nejc Čeplak is going to discuss lack of singularity como proyecto.
Okay, thank you very much. Thanks for the organizers for giving me the opportunity to talk. I'm going to talk about possibly the last point that was raised in the previous talk, and that's how to see black hole singularities just using the CFT in ADS-CFT. This is based on this paper that appeared this April with some of my collaborators. In particular, Sam is in the audience, and he's going to be applying next year, so keep an eye out on him if you want someone who knows how to do Mathematica code really, really good. So the upshot of the talk, because it's late, and I want to just give you a brief summary of what's going on. The object in question is going to be a two-point firm of correlation functions of scalar operators of conformal dimension delta. I want to use this calculating in holography. And in holography, I can just standard for a finite delta. I can start using the OP expansion. And yeah? I'm too energetic. Oh, sorry. I can just shout. Sorry. It's excitement. Let's go. I'm the final one.
Okay, should be fine.
Okay. Sorry. Does this count towards the time, by the way? Just kidding. Okay, so if you define a delta, what you're going to do is you can do the OPE, where you bring the two probe operators together. There's two sectors that you can find. The first one is the stress tensor sector, which contains the identity, the stress tensor, and the multiple stress tensors. And the other one is the double trace sector, where the exchanged operators are just the composites of the probe operators stressed by appropriate with appropriate derivatives. But what we also know is that if you take the delta to be large, then the correlation function just reduces to a geodesic. And in particular, if I look at a two-sided correlation function, which is calculated using a double-sided black hole with each operator inserted on a different side, there exists a real geodesic which connects the 2 points and probes the interior of black holes. This is a little bit of a problem because this geodesic cannot probe the entirety of the boundary for all Lorentzian times, but actually there exists a critical point in which the space-like geodesics approaches a null geodesics, and associated with this is actually a null singularity in the correlator. Unfortunately, this singularity is should not be here. This is not allowed by just thermal field theory. This is, by the way, a complex value of the time at which this happens. So gauge gravity or ADS-CFT knows that this shouldn't happen, and I'm going to show this in a couple of slides how this is resolved. But the information about this is that this null singularity, which we also call the bouncing singularity, contains information about the black hole singularity. It's still available in the two-point correlation function, albeit in a little bit of a subtle way, using analytic continuation in the second Riemann sheet. I'm foreign, I'm sorry. But what was unknown so far is how this black hole singularity is encoded in the OP data, in particular in the stress tensor sector and the double trace sector. And what I want to show today is, what I want to convince you is actually the information is encoded in the large number of exchanges of stress tensors. And if I resum the OPE of the stress tensor sector near the singularities, what I find is that exactly singularities that you find from the black hole, from the bouncing singularities at finite delta. What this means, the upshot of this talk is that the stress energy tensor sector of holographic correlation functions knows about the black hole singularities. Okay, now for the next how many ever minutes I got left, I'll try to convince you, I'll try to show you some of the consequences of this. Okay, as said, the central object is a two-point correlation function in holographic theories at finite temperature, 1 over beta. Throughout this talk, I'm going to be using tau, which is complex. The real part is Euclidean, and the imaginary part is Lorentzian. And the operators that I'm going to be using are scalar operators, which I assume are dual to many coupled scalars in the bulk. And so the bulk geometry I'm going to be using is just a planar black hole, which means that the boundary theory is just flat R3 multiplied by time. As I said before, if I take the delta to be large, I can use the WKB analysis to just show that this correlator actually to leading order can be given just by sum over saddles, which in this case are geodesics, which connect the insertion points on the boundary. And in particular, I'll be interested in two sections. The first one is the Euclidean section, where I take the Lorentzian time to be 0, and then I'm looking at geodesics, where just connect 2 points on the boundary disk of the Euclidean section, which is just the cigar, even in ADS. I label the geodesics with energy, because I have a null isometry along the time-like direction of the geometric. And if energy is equal to 0, then the geodesic just goes across it connects points at tau is equal to beta over 2. If I increase the energy for positive values, I probe small and smaller values of tau, so that the positive infinity limit actually is the near coincident limit of the Euclidean section. If I take the energy to be negative, I just look at values of tau is greater than beta over 2 but smaller than beta. On the other hand, I can look at specific values of tau as beta over 2 plus I tau L, which is exactly the double-sided correlator. And then I find the real geodesic, which connects these 2 points and probes the interior of the black holes. And as I said before, if I increase the energy here, which now I increase it in the imaginary direction, so the energy in this case is imaginary compared to the value for the Euclidean section, instead of just probing this entire Lorentzian section up and down, what I find is I go to a critical value where the space-like geodesic approaches a null geodesic, which just bounces in and out of the singularity, because in the case of ADS Schwarzschild black hole in 4 or higher dimensions, the Penrose diagram is slightly curved. So you go in, you probe the singularity, and you go directly out. Unfortunately for this case, if this geodesic did contribute to the correlation function, we would find, okay, I don't know if I can point, but anyhow, we will find that the correlation function diverges at this critical value, which is a complex value, it's not that important, but this is not allowed for just values for just in terms of ordinary thermal quantum field theory. ADS-CFT knows about this, and it knows about this in a very particular way. If I expand my correlator, and if I expand my proper length around beta over 2, I find a branch point with a power of 4 over 3, which means that around this beta over 2, which was just the geodesic which goes across here, I find 3 different branches. One of those branches is the real geodesic that I showed you before, and the 2 other branches in the Lorentzian section would correspond to complex geodesics, which I cannot show in the Lorentzian patch, but are actually there and they contribute. And if I now do the WKB analysis exactly, which was done by the papers over there, and if I look at the contour of steepest descent, look at all of the saddles that contribute there, I find that these 2 geodesics are the leading order contributions that you find. And that this real geodesic, which I showed you before and contains the singularity, actually never contributes. So the upshot of this is that the E2 branch, which I label here E2 for reasons which are not important here, which contains the information about the Banks singularity, actually never contributes. Not even if it's subleading, it never contributes. It doesn't lie on the contour. So the information is still available through analytic continuation from the other 2 branches, but it's subtle. It's subtle. And for the other point, I'm going to be showing what, if you do this analysis concretely, what happens is that you will find that this first branch is dominant on this side for beta tau is smaller than beta over 2, and the other branch is dominant for the other side, while in this section, both of those contribute at the equal value. Okay, this was the story. This is the old story for balancing geodesics, which is by now 20 years old. Now we want to see, okay, how is this encoded in the OP data? Again, I decompose my thermal correlation function into the stress tensor sector and the double trace sector. I will stress just out the exponent that you see in terms of tau over beta. Those are the conformal dimensions of the exchange operators. The interesting things are these OP coefficients lambda n and dk, which are resummed operators over all the operators which have same spin at the conformal dimension that can be exchanged in the channel. There was an impressive paper by Fitzpatrick and Huang, which recently gave us a way of calculating just the stress tensor coefficient by solving in a perturbative way the holographic equation in the black hole bulk. And what you can get is you can find the stress tensor sector just as an expansion of tau over beta. So you're just calculating the correlation function order by order, and you find these horrible coefficients, which are just, in principle, you don't need to know what they are. I just want to show that there's some polynomial divided by some poles. Now, perhaps this might be slightly non-enumerating, so perhaps it's slightly more important to show what happens if I fix delta to be a finite value, and then just look at what happens when n gets increased. What you find is there are actually two different behaviors. There's some behavior at the beginning, and then there's some n star value where there's a slight crossover. Now, initially we thought that this is, okay, some numerical error that we're making, it's not converging, but actually this has a fundamental reason. Namely, this crossover happens exactly the value where the double traces start to contribute. I would like to stress out, we're still calculating just the stress tensor sector. We don't know information about the double traces, but even the stress tensor sector knows through this value, through this change, where the double traces start to contribute. And that the double traces are important is actually can be seen by the fact, jumping off of what Ellie was talking about today, is that just the stress tensor sector by itself does not satisfy the KMS condition. And you can see this by just checking whether the correlator in the OP expansion is symmetric around beta over 2. It's not. Therefore, at least for beta is greater than, tau is greater than beta over 2, double traces are important to ensure KMS condition. This can also be seen, by the way, in the example of name which I forget. I'll recall it later. There's a toy example which you can see. Anyhow. Okay, what do we want to do now? I want to fix delta to a finite value, and I want to see what is the asymptotic value of the OP coefficients that I just calculated. Sheet. 5 minutes, I said. And what you can see is that you can find the asymptotic value. The asymptotic value has this nice formula which allows us to resum the OP coefficient. And this OP coefficient, the OP series for the stress tension sector, you get some logarithmic divergences, and you find that these divergences are exactly the same values as the ones predicted by the bouncing singularities up to some reflections. Not only that, but you see this exponent is very similar to what you found for the geodesic analysis as well. But I just want to stress this out. I want to stress this, that even at finite delta, the stress tensor sector has a divergence at the same location as the bouncing singularity. So this means that at finite delta, the stress tensor sector knows about the curvature singularity in the bulk. Okay, I just told you that this singularity should not exist. So what is going on? First of all, this is just a singularity in the stress tensor sector. What this means is double traces are still there. So double traces better cancel out the singularity. Not only do they have to cancel the KMS, they have to ensure the KMS, but they also have to cancel out this. But secondly, you would say, okay, if I take the delta to infinity limit, I reproduce the singularity from the bouncing geodesic. But this assumes that I can take delta to infinity limit after I resum the OP, which is not correct, because remember that this n star, which knows about when the double traces come, is linear proportional to delta. So if I take delta to infinity at the beginning, I'm summing over a completely different information. And if you do this exactly, if you do this by taking delta to infinity first, you reproduce the proper rank, which is the right way to take delta to infinity limit, and you find that the stress tensor sector, by itself, for tau is smaller than beta over 2, completely reproduces the geodesic result. So for tau is smaller than beta over 2, you don't need double traces at all to reproduce the geodesic. We're not the first one to point this out, but it's important to stress it. And what happens to the singularity? If I do the asymptotic analysis for these terms, what I find, unsurprisingly, is exactly beta over 2, which is smaller than the critical point. So at infinite delta, you don't find any bouncing singularities. Okay? Now this is cool. This allows us actually to say something about the double traces, even though we cannot calculate anything. Namely, the decomposition, if I take the decomposition and just take the ratio of double traces and stress tensors, I'll get this factor, this leading factor. So if delta goes to infinity, for any tau is smaller than beta, I would just say that this vanishes. So double traces, in principle, at large delta limit should not be important at any value of tau. But as we saw before, there is a branch point at tau is equal to beta over 2. So there should be something different happening. So this cannot be true. And the idea in this key assumption that goes into this formula is that you can take delta to infinity limit after you take the OP, which is not true because we know from our analysis, holographic analysis, that the tau is beta over 2, something different happens, and what happens is that the double traces become important. Or in other words, if you want it more mathematically, the OP is not uniformly convergent for all delta, in particular, in delta goes to infinity, for tau is greater than beta over 2. And in order to get a complete and a valid result, you first need to resum the OP to get an analytic result and only then take delta to infinity limit. Okay. This has a very interesting consequence. I've just told you that the delta goes to infinity limit. I have to include the double trace contributions where they really become essential to ensure that the correlation function is correct. But remember I talked about the branches. I told you that the first branch, E0 branch, is important for tau is smaller than beta over 2. I showed you that the stress tensor sector completely reproduces the tau beta over 2 geodesic length. So what we can do is we can identify the first branch with the stress tensor contribution. At tau is beta over 2, and for all the imaginary values, we saw a branch cut and we saw that the double traces become important. This kind of suggests that the double traces are inherently linked and should be identified with the second branch, and delta goes to infinity limit. And so what we see is we get these two complex branches, two complex contributions to the geodesic that we saw in the geodesic analysis, can have a nice interpretation in terms of sectors of the OP the composition at tau is tau is 0. Okay, the summary. I have shown that the stress tensor sector contains information about the black hole singularity. You might be asking, why am I saying that the singularity is contained within the stress tensor sector, not the double traces, even though I told you that double traces should have the same singularity to cancel it out. And the reason for that is that the stress tensor sector is somewhat universal. You can think of the stress tensor sector as containing information about the exchange of a large number of gravitons. And it would kind of naively make sense that the exchange of a large number of gravitons knows about the curvature singularity of your bulk. And it's somehow universal, whereas I can change what the probe is, and I should still expect the same behavior in my correlator. But nonetheless, double traces are important, especially if tau is greater than beta over 2. First of all, to ensure that the correlator satisfies the KMS condition, and to cancel the bouncing singularity of the stress tensor in the full correlator. And what I've also shown you that when delta goes to infinity, the stress tensors and the double traces can be identified with different branches of the geodesic solution that we found in the geodesic analysis. Why are we doing this? Why is this interesting? Because it gives us a new approach to analyze bulk curvature and singularities in using ADS-CFT. And in particular, it would be interesting to see if I had a CFT without any holographic interpretation, or if I had some CFT where I can resum the stress tensor sector, what would I see? Perhaps related to what we talked before, what was in the previous talk, what was talked with Michael was talking about, and so on and so forth. And it also gives us some new information about some new directions in which to study. For example, what happens with alpha prime corrections, G Newton corrections, or if you want lambda corrections and large N corrections. What happens if I had matter fields? What happens if I had a star? A star still is described by ADS-Schwarzschild far away. So it should have about the same stress tensor sector. What is the difference there? And what happens if I have other boundary manifolds? This is something that we're working on right now as well. So hopefully, Eurostrings 2025. Okay, that's all. Thank you. I'm very happy that all of this is recorded, by the way.
So, to what extent is actually sensible to separate the correlation function into a double trace and a stress tensor case? In particular, if the operator is of integer scaling dimension, how do you disambiguate between the double traces and the stress tensor?
That is a very good point, and it's not very clear how to do it, so you do it in practice for non-integer delta. I think in holographic theories it makes sense, you can always separate them, even if it's, but you just don't know, so if you had an integer delta, it would be ambiguous of which contribution, because you get information for each values of tau, so you wouldn't know which one is which, so you have to do some disentangling. But in principle, what you assume is that the contribution is some relatively smooth function of delta, so you'd be able to, like, if I shifted a little bit, you should be able to distinguish between those two functions.
If I can abuse another question, to what extent the knowledge of the singularity is not just a product of analytic continuation? Meaning you are taking large delta, and you did the analytic continuation of the geodesics.
Yeah.
And as you show, if you do it correctly, if you consider the Stokes phenomena correctly, you never see the bouncing singularity.
Precisely.
So to what extent would I even expect that? Another way to put it: if I change the interior of the black hole, will I see something? If I consider something like the Kastner universe, that's what you presented.
That is a very good question. I would like to know that as well. So perhaps the information is it's very mysterious why this happens, right? So because in principle, as you said, right, the geodesics, the correct geodesics that give you the correlation function, they don't know about this. So in principle, this wasn't a guarantee. It was just like the reason why you look at the asymptotic values of your OP coefficients is because the divergence, the radius of convergence tells you where the first singularity is. And by, I don't know, sheer luck, or whatever you call it, the singularity is still there. So we're trying to figure out, okay, so this is the simplest example you can find. Flat space, black hole in are free asymptotically. What would happen if you now start to make it more complicated? So it would be interesting to see. Those are very important questions. For example, what is the mechanism that really gives you this black hole singularity? The information we don't know yet, but it's still to be determined.
Yeah, so maybe I'm repeating the question first in a different way, or maybe you already explained it and I missed it. So if I take an example of holography where we know exactly where what the field theory is, for example, n equals 4 super Young-Mills, and suppose you could do an exact calculation at finite temperature.
Yeah.
Would you say that then from these correlators you can read off the Kastner exponents behind the horizon in the bulk, or I'm confused about what the claim is here?
The claim is, so, okay, the way that, the first question is, how would you calculate the OP, the stress tensor OP, right? So in principle, if you have a holographic theory, you use the bulk.
No. I'm saying, suppose in the field theory you could do any the field theory is completely well defined.
Yeah.
In principle, there's an answer.
Yes.
It may be impossible to compute it, but suppose you could.
Yeah.
Would you claim that from this you can extract, and you're at large n and strong coupling, so there's a well-defined dual. Would you say from this you can extract the Kastner exponents behind the dual horizon or not?
I don't know if I would say Kastner exponent. So I don't know how much information is contained. The only information I know is there's this critical exponent which contains some information about the singularity. The hope is there is some information about the singularity in there, and I would claim that some information is. I'm not entirely sure about whether this specific detail is encoded there. So but I would say, presumably yes. I hope so. Would be my answer, but I don't know is the cautious answer into this question.
Okay, maybe I'll try to catch you.
Yeah, no, absolutely. Yeah, go.
Yeah, very quick question. Like when you consider the OPE, you are considering the theory at finite temperature on the thermal manifold, which is a flat space component times a thermal circle. If you've ever thought about doing the same on a geometry which is a sphere,
Yes,
times S1.
we're doing it now. Yeah, we're doing it now. So if you have a sphere, in principle, things don't change that much. In principle, you still have the same critical point, so you should see the same thing. It's just slightly more complicated because both on the CFT side, you have additional exchange operators. So in the flat space, a bunch of things fall out. On the CFT side, on the bulk side, it's instead of having one parameter, you have a two parameter. So trying to find a singularity for two, it's slightly more complicated. But it should be in principle work. And we have some partial
you
results.
think that it's only a technical difficulty
Yes,
in more difficult OPE, but the result should be the same.
Yes, I think we also already have some partial result, and we show that this works. So for the sphere, it should work. If it's anything more complicated, it would be interesting to see what happens. And yeah.